This lecture was supposed to be done going through the mountains of Colorado, but my camera wasn't working. So I'll just do it right now. This is everything I know about physics and chemistry. So where do we begin? Everybody knows about electrons. Do you know that they found out about electrons using a vacuum tube, which was an evacuated glass tube that had a potential difference in it? So you have like ions on the two sides, and through the vacuum they fly. It might be that they're excited, I'm not really sure. And they found the mass of this electron through bending experiments using a magnet. Now, you've heard about electrons, and now we're on to protons. There's scattering. Rutherford scattering, look it up. See, what happens is you send protons at a foil. I think it was a silver foil. And they found out that some of them diffract and some of them even bounce back, but some go through. So they found out that the atom is somewhat hollow. And they are able to figure out forget that. You are able to figure out if you send protons through an evacuated tube using sometimes they use plasma, which is the highest energy state of matter, to accelerate. They don't really use that in accelerators often. But they use electromagnetic or magnetic pulses. And there's three types of general accelerators. There is the synchrotron, which is more powerful than the cyclotron. And then there's linear accelerators. The cyclotron is a circular track. Now, you have to know the fields of science. So, relativity is the field of going really fast. Okay? Like near the speed of light, which is the supposed speed limit of all matter in the universe. Remember, we are on a moving Earth. So, there's these things called tachyons, and maybe even neutrinos go faster than light. Because neutrinos, you can't figure out what they're doing because you can't measure them. So tachyons are hard to create too. So we have the proton, neutron, and electron, but each of those have an antiparticle. Well, I'm not sure if neutrons have an antiparticle. I suppose they do. The positron is the anti-electron. It has this, well, okay, I'll say this. There is a negative charged massed proton, and there is a positively charged massed electron. And both. So, exotic matter is the field of non-electron neutron and proton chemistry. Most of those things are very short-lived. Now, I have an idea to make an accelerator that would be of neutral matter. See, neutral matter is very hard to accelerate because you're trying to accelerate both the electron and the proton using a magnet. It won't go anywhere. So here's a side note. There was this anvil at Harvard University that they used to make metallic hydrogen. See, metallic bonds are where the electron flows freely in the vicinity of that atom. So you have the two, and dihydrogen would usually be a covalent bond, because if you know anything about chemistry, usually they follow rules like the octet rule, I think it's called, where you want 2 electrons due to the energies, and then in the next ring 8 to be stable. But when you're looking at science, stable or unstable, they say that protons are probably decayable, but it would take more than the length of the universe. But they have actually experimented on this. They made a huge tank of water, and they wanted to see if a proton would decay. So what they did is they calibrated for as many atoms as, I think it was atoms. It was water. So they made detectors, and I'll get into the detectors later, of, to pick up a proton. Now, how would you pick up a proton? Well, I'll tell you. You would pick up a proton through bubble chambers or electromagnetic sensors. There's some gas, if it causes friction, which an electromagnetic particle does with other electromagnetic particles, or repulsion. See, you can probably pick it up by sending a proton at maybe a copper wire, for instance. And when you do that, if the copper wire oscillates, and I'm sure they can do this, you know that, well, you know it because it'll come towards it. You can probably pick up the speed in the wire. Now, I'll talk about electricity for a little bit. So, electricity is an electron movement within a material. So, it's a metallic bond type thing, but there's pressure, and there's 2 types of current. There's direct current and there's alternating current, and that's where you get motors. You get a spinning magnet, and depending on the apparatus, you get them to go back and forth. Now, a chemical battery, for instance, is going to be direct current. So the electrons are going to flow through. And usually they use a bath, and they use 2 metals. And you can see chemical reactions occurring at the anode and cathode. The cathode is the positive one. Remember, C, cathode. Anode, positive. And anode, negative. Negative for the positive. Well, double negative. So, these magnetic particles are attracted to magnets, which are activated flint, right? Activated flint. Well, they're known as ferromagnetic materials. There's many, Well, you can look it up. There's many of them. Then there's materials that are piezoelectric. So you put pressure on them, or you induce a current in them, and they either, when you put the current on them, compress or shrink, or expand, or when you compress them, and some of them do both, or expand them, they put a current on. Actually, I'm not sure if there's any that if you expand them, it happens. So, you have these... Well, I'm not really sure where I should go. For interest's sake, let's go back to relativity. So the speed of light is approximately 298,000 meters per second. So, for interest's sake, in the atom, some lanthanide and actinides of the upper numbers are moving very quickly, relativistically. So those aren't going to follow regular rules. Those are going to be relativistic in nature, their chemical bonding. One second, I'm thinking of where I went before that. It would be easier if I had someone reminding me. So, yeah, there's also things that when you start them on fire, you heat them, they become electric. And there are things that when you obviously burn, they go on fire. That's combustion. That is photons. Now let's get to lasers. See, lasers are different than regular candlelight, for instance. The photons come, and there's a difference between ultra cold lasers and regular lasers. See, what happens is there's these energy orbitals in a atom, a non-exotic atom. And I guess there are probably orbitals too in an exotic atom. But as I said, those are really likely to just collapse, decay. Something will fall into the nucleus. It'll cause a crazy kind of quantum reaction. So you have those things. I forget what those things are. So let's go over the matter. There's electrons, and in that class there are leptons. Now you can look up a quantum particle chart. There are leptons, and then there are, I forget what they're called. They have two classes, the baryon and the meson. Maybe it's not meson. It starts with an M. It's diametrically opposed to the meson. So you have the baryons, which are composed of quarks, which are composed of gluons, which obey color charge. Now, color charge, like electromagnetics and gravitations, those are forces. So you have those. Those are two separate forces. And then you have the electroweak, which they say at the beginning of the universe, some cosmologist reasoning says the electroweak and the electromagnetic at the beginning of the universe were one. They separated, they disentangled, whatever. I don't know anything about that. And so you have the electroweak, and you have the strong nuclear force. Now, the strong nuclear force is a very short-acting, in-distance force. It holds the atoms together because the proton and the neutron have different spins. And well, they say they don't know why. Well, maybe that's not true. Maybe neutrons don't have don't have opposite spins of protons. They do have spins. They have a magnetic moment. And anyways, the proton should repel. They don't at a short distance. That's why you have nuclear fusion, nuclear fission. You send that proton in an accelerator fast enough, and it'll either combine or it'll break apart, and there'll be radiation, heat, photons, yes, released. And there are other particles, smaller particles. I think often in nuclear reactions, the proton will decay when it is in a fusion reaction or a fission reaction. What does the proton decay into? Well, the proton is a baryon. So it is composed of quarks, but not antiquarks. And so the mesons, I believe they were, are composed of pairs of quarks and antiquarks, which are composed of gluons, which obey a color charge. And now they think that gluons, at least according to the model right now, are both the charge carrier and the charge particle. That doesn't make sense, but that's how they're dealing with it. So we have this color charge. You can look into that. It's very complicated. I actually don't really understand it right now. I would just like to throw in that you can't find gluons in nature alone. Why? The why may be that because of the movement of the Earth, these small particles are getting knocked around in reactions. But they say that a gluon will, with its distance, increase its force, its attractive force to another gluon. Wrap your mind around that. Now, there's probably out there already some model. Anyways. I don't know if I said about my reactor, the Harvard anvil, my idea to smash an exotic atom that has an electromagnetic either core or radial whatever, and accelerate it, use that electroweak because protons, neutrons, and electrons all obey the electroweak, I think. And I'm pretty sure. I think I looked into this. And yeah, accelerate them, collide them. You never know what you're gonna get. You might get some weird stuff, and that would be a whole new field. So you have that stuff. What else? Weber bars. These are, and torsion balances. I believe a torsion balance is probably made out of aluminum, like a Weber bar. A Weber bar reacts to gravitational waves. Now, this is controversial, but the Weber bar reacts to, say, a colliding pair of black holes, and it'll oscillate, and then the piezoelectric, that crystal, the quartz may it be, will send out an electromagnetic pulse. These Weber bars are very big. Now, torsion balance, it was invented by Walter Cavendish, which was a balance beam that I hope, I don't know if it's ever been done in a vacuum. You could calibrate, shield the electromagnetic waves, put the electrical apparatus inside it, put a neutral big mass next to a lever, and a same material small mass. There you go. Then do we know if gravitation is a force there? What's going on? Well, you don't actually know for sure. You have to deduce these things. So it could be something coming out of the vacuum, some really small particle getting sucked up in there. You never know. Now, I'll go into some like fringe stuff. There's stuff called ball lightning. And they actually don't know what ball lightning is. It's these balls of lightning. Supposedly, they've been seen. They're really hot and they explode. Now, if you want to get into cool chemistry stuff, I'll just give you a short rundown in case you have never had any chemistry class or whatever, or you weren't paying attention. So you have chemical changes in the substance, and you can have different electrical conductivities, different magnetisms. You can have explosivity, an explosion. You probably know what that is. So you have those things. And what else do you have? You have luminosity. Oh, I should get back to the lasers. See, a photon is actually of two parts, and you can split it of a magnet. But these ultra cold photons, there's always one spin right, spin left. But you don't know which one's going to be spin right and spin left in ultra cold lasers. Now, you do at warmer temperatures. But I think it is that a candle, you should look into this. A candle doesn't send out these discrete packets. I know that either the wavelength or the frequency you can get really accurately with a laser. It will be discrete. You can't get that with a candle. Now, a laser is a chemical or atom trapped in a box. Now, this goes back to the orbital theory. See, there are different orbitals, and they're discrete. They're discrete distances, I should have said, distances from the nucleus. And you excite them, they go discrete differences. That's discrete, if you haven't heard it. It's not like that. It's like here or here. But you know it's actually moving between them when it jumps. And you excite some things, it jumps out. You excite some things, they go in. Going in would be an endothermic reaction. That's heat taking in, I think. I don't actually know if it's a single atom and whether they'd call it endothermic, or even if it would release more photons afterwards. This gets really complex. Only a physicist would know. But so usually what happens is you heat a atom or a molecule, and oh, this is cool. I'll get to the cool thing in a second. It jumps up and then it comes back. But when it comes back, it emits the discrete type of light. And so because it does, we have these things called spectrometers. And spectrometers are prisms that break up the light into, say, like a rainbow. But since an atom or molecule has discrete emission spectrum, you only get certain things, and you might not be able to see them all with your eye. I think I've gone over everything. Particle accelerators, they're smashing things together. Remember that. And there's some really, really amazing things that they've done. Like they've sped protons up towards the speed of light, or electrons, positrons. Now, I think it's iridium. It creates positrons. It ejects positrons. Now, this is kind of an exotic particle. And they also make them in particle accelerators, collect them. They collect them. And they've done some stuff, rapid cooling with, I think, lasers, traps. They find these really insanely short, like less than you could even count, using this engineered brilliancy, decay products, or maybe bonding products and then decay products, but they always decay. Now, neutrinos are thought to go through all matter. Neutrinos, I believe, make up leptons. Yeah, I think so. Now, there's an experiment to pick up neutrinos in, I think it's the Red Sea, and so they're actually looking under the water, and they have like cameras set up to make sure there's nothing changing it. Neutrinos from space. They want to pick those up. They think neutrinos can go through the Earth, but they're looking for little signs of light. The little evidence that it was there and changed something in the water. Now, I'm not going to remind anybody. Just, if you do that, just control for the cameras, okay? And, yeah, see, maybe I haven't gotten it all, probably not. I was just reading that you can, change molecular, like molecular solid crystalline structure. You can soften it or weaken it with a laser. Not a magnet, a laser. What else is some stuff? Well, what I want to get you away with is that you don't have to be scared of science. They know a lot of poisonous chemicals, and there are not very many of them. There's like 50 to maybe 75, maybe 150 that will come as fumes that'll kill you. But these tiny stellar originated or whatever cosmic radiation are going through our body every single moment. Tons of them. And it's pretty cool. I think it was Einstein. It might have been it was Einstein. He sent this other guy. Funny story behind the two of them, but I'm not going to go into that. Up a mountain. No. Maybe that was the eclipse. Maybe that was the fact that light bends around planets, or not eclipse, but light in space bends around celestial objects. Light has gravitational attraction. That should be, I would say. But I guess it was the Japanese, I think, scientists who sent people up a mountain, and they found these clusters of exotic matter. It was a very small particle. Now, there's Bose-Einstein condensate. That's when it's really cold. You make it really cold and the matter declumps and becomes more, or exactly, graded, I would say. Isolated or individualistic. And in plasmas, you have in solids, you have the crystalline structure. They're not moving. In plasmas, the atoms break up. So that would be protons and neutrons and electrons just flying everywhere. That's what's happening in the center of the sun. It's a plasma. Now, I should say that the Harvard anvil that I talked about, that they used to make metallic hydrogen, it makes pressures, well, it broke, I guess. It makes pressures of the core of the Earth. So it's possible that metallic hydrogen is of this Earth. And I'm going to try and remember what metallic hydrogen was going to be used for. I actually don't remember. So, then there's like the nanoscale stuff. And that's like you have these little atoms, and you can like pull water around with the, I think it's steel. These, like, the size of the steel changes how it interacts with the water, and you can drag the water around because the steel's in there. And that's chemistry. There's electron microscopes. You can see the electron cloud. There's electron tunneling microscopes, which are even more powerful than electron microscopes. Now we'll get into, I'm going to do architecture and what I know of biophysics, but biophysics is going to be pretty quick. So positron emission technology. You put this radioactive substance in you, it's kind of dangerous, and the positrons emit, and they look at your brain, picking up the, I guess I haven't finished, I should say, with, accelerator detectors, which are my favorite thing. See, they have photo plates. If you don't know how a photograph works, or how about I should say the camera obscura. The camera obscura works because the light actually goes like that. Whatever. It splits. You look through a doorway. You might never have noticed. And then there's the quantum physics experiments where you, I can't remember what it's called, but it has the discrete clumps. Now, it may fan, but there are discrete amounts in each place, and you can look up how much of each. Now, a photosensitive chemical reaction, or a photosensor, is a reaction induced by light. You get those in old cameras. Now, there's spark. Now, this is really cool. There are spark chambers. So if a certain type of particle goes to the chamber, the electromagnetic stuff will make a spark. It'll pop. And I've heard that particle accelerators won't ever start on fire. That's what somebody on the internet told me. But you have these, so they actually, and some things in a particle accelerator, they'll spin in a helix due to magnetic magnets on the sides. Well, so I can't really get into that because I actually don't have the data, so I can't work on it. But so you have these accelerators, and you have the tracks, and different chambers, different electrical devices, different materials. Well, those would basically be electrical devices, but whatever. Am I missing anything? Oh, well, let's just do Newtonian physics. Fuck. Moment of inertia. What it spins around when thrown. That's due to the mass in it and the gravitational pull of the Earth and the object acting on each other. Now, this is a funny thing that I kind of cleared up for myself. See, when you have a string at an angle and it has a weight on it and there's another string, and you use trigonometry to figure out how much stress, you divide it by 2, you use the equivalent trigonometric stuff, but that's not actually what's happening. It's not this. It is the stress in the string, but it's due to the moment and the gravity. See, when you have the 9.81 meters per second approximate gravitational acceleration per second squared, etc. Newtonian physics is pretty cool if you want to be a builder. What else? Centrifuges spin really fast. The more massive stuff falls to the bottom. Well, not the bottom, the outside. Oh, yeah, in some accelerators, they centrifuge the stuff at the end. I'm pretty sure. What else? That's it. That I know about, I think. So, yeah. Peace out. Thank you.